Something is coming. Right now, as you watch this, an interstellar visitor is racing toward our inner solar system, carrying metals that shouldn't exist on any natural comet. The scientists who discovered this call it extremely puzzling. But here's what puzzles me even more. Why does this frozen visitor from another star system contain nickel and iron in ratios that mirror industrial alloys? Stay with me, because what I'm about to show you challenges everything we thought we knew about interstellar objects. And by the end, you'll understand why some researchers are quietly asking a question that makes everyone uncomfortable. Is this thing natural, or could it be something else entirely? Let me paint you a picture. It's July 2024, and the Hubble Space Telescope is tracking an object designated 3I/ATLAS. This isn't just any space rock. This is only the third confirmed interstellar visitor we've ever detected, and it's behaving in ways that make no sense. When astronomers first spotted it, they expected the usual: ice sublimating into vapor, maybe some dust. The kind of activity you'd see from any comet approaching the sun. But when they pointed the UVIS spectrograph at the Very Large Telescope in Chile toward this visitor, they saw something that shouldn't be there. Nickel. Abundant, consistent, impossible nickel. Here's the thing about comets that most people don't understand. They're frozen time capsules from the early solar system, composed mainly of ice, dust, and rock. When they get close enough to the sun, the ice sublimates directly into gas, creating those beautiful tails we see in photographs. But metals like nickel and iron, they require temperatures so extreme that comets simply can't reach them at the distances where we observe these objects. Yet there it was, nickel everywhere. Not traces, not hints. Abundant, unmistakable signatures flooding the spectrometer readings. But that's not the strangest part. Stay with me here, because this is where the story takes a turn that will make you question everything. The nickel appeared consistently across 6 different observation periods. 6 separate intervals as the comet moved from 3.14 astronomical units to 2.14 astronomical units from the sun. Every single time, nickel dominated the readings. Iron, however, iron only showed up when the comet got closer than 2.64 astronomical units. Think about that for a moment. Nickel everywhere, but iron appears late. This isn't how chemistry works in our solar system. This isn't how it worked with the previous interstellar visitor, 2I/Borisov. This is something entirely different. I've spent weeks diving into the research papers, talking to astronomers, analyzing the data, and here's what keeps me awake at night. The nickel to iron ratio in 3I/ATLAS doesn't match anything we've ever seen in nature, not in our comets, not in other star systems, not anywhere except in one very specific place: industrial alloys. Now, before you think I'm jumping to conclusions, let me be clear. The scientists publishing this research are being extremely careful with their language. They're using words like puzzling and anomalous and extreme properties. They're proposing natural explanations. Maybe it's a fragment from a metallic planetary core. Maybe there are chemical processes we don't understand yet. Maybe the heating patterns are more complex than we realized. But there's one voice in the scientific community that's willing to say what others are thinking. Ava Loeb, the theoretical physicist who's never been afraid to explore unconventional possibilities, looked at this data and made a statement that sent ripples through the astronomy community. The detection of nickel without iron is only known to exist in industrially produced alloys made through the artificial carbonyl chemical pathway. Artificial, that word hangs in the air like a question mark over everything we think we know about interstellar space. Now, I want you to imagine something. Imagine you're an astronomer who's dedicated your career to understanding comets. You've studied hundreds of them. You know their chemistry, their behavior, their predictable patterns. Then along comes an object from another star system that breaks every rule you've ever learned. It's carrying metals it shouldn't have, in ratios that don't occur naturally, behaving in ways that contradict decades of established science. What do you do with that information? This is exactly the position astronomers found themselves in when the UVES spectrograph data came back. The European Very Large Telescope in Chile had been trained on 3I/Atlas for months, collecting spectroscopic data that would reveal the chemical fingerprints of whatever materials were sublimating from the comet's surface. Spectroscopy is like cosmic DNA analysis. Every element absorbs and emits light at specific wavelengths, creating unique signatures that tell us exactly what we're looking at. The signatures they found shouldn't exist. Here's what makes this discovery so unsettling. We've had two previous interstellar visitors, one I/Oumuamua in 2017 and two I/Borisov in 2019. Oumuamua was bizarre in its own right, showing no cometary activity despite its trajectory suggesting it should have developed a tail. It also exhibited strange acceleration that couldn't be explained by gravitational forces alone. Borisov, on the other hand, looked remarkably similar to comets from our own solar system. It behaved predictably, developed a normal tail, and while it did show some traces of nickel, nothing like what we're seeing with ATLs. 3I/Atlas is different. It's not just unusual, it's unprecedented. The international team of researchers who published these findings didn't mince words in their conclusions. They stated that 3I/Atlas exhibits extreme properties in the early phases of its activity with regard to the production rates and abundance ratios of nickel and iron. They noted that the object remains exceptional compared to solar system comets due to its high asymmetrical production rate of these metals. But here's the part that should make you pause. They also wrote this: at the distances at which comets are observed, the temperature is far too low to vaporize silicate, sulfide, and metallic grains that contain nickel and iron atoms. Therefore, the presence of nickel and iron atoms in cometary coma is extremely puzzling. Extremely puzzling. That's scientific language for we have no idea what we're looking at. And we're not just talking about trace amounts here. The production rate of nickel atoms from 3I/Atlas is extraordinary, higher than any comet in our solar system, higher than Borisov, higher than anything in the scientific literature. This object is practically bleeding metal into space as it approaches the sun. Now imagine you're not an astronomer. Imagine you're someone who designs spacecraft, someone who works with metal alloys, someone who understands industrial processes. You look at this data and you see something that looks familiar. You see nickel without iron in the early stages, which is exactly what you'd expect from certain manufacturing processes. You see abundance ratios that match artificial production methods rather than natural stellar formation. This is where the story becomes uncomfortable for traditional astronomy, because if this object isn't natural, if it's the remnant of some industrial process from another star system, then we're not just looking at a comet. We're looking at evidence of technology. Advanced technology from a civilization that existed long before our sun even formed. The implications are staggering. We're talking about an artifact that has traveled through interstellar space for potentially millions or billions of years. A piece of engineered material that has somehow survived the journey between star systems and arrived here just as humanity developed the technology to detect and analyze it. But let's step back for a moment. I don't want you to think I'm claiming this object is definitely artificial. What I'm saying is that the chemistry doesn't make sense if it's natural. The timing doesn't make sense. The abundance ratios don't make sense. And when multiple lines of evidence point away from natural explanations, we have to consider alternatives. This is the same intellectual courage that led to the discovery of exoplanets, black holes, and gravitational waves. Sometimes the data points to something that challenges our fundamental assumptions about how the universe works. The question is, are we ready to follow the evidence wherever it leads? As 3I/Atlas continues its approach toward the inner solar system, we're about to get our best look yet at an interstellar visitor. Later this week, as it passes within 29 million kilometers of Mars, NASA's Mars Reconnaissance Orbiter and ESA's Mars Express mission will capture images at unprecedented resolution. We'll see details that Hubble simply couldn't provide from Earth's distance. What will those images reveal? A mundane chunk of ice and rock with unusual chemistry, or something that forces us to reconsider our place in the galaxy? The metal-rich visitor from beyond our solar system is about to give us answers. Whether we're prepared for those answers, that's another question entirely. The UVIS spectrograph doesn't lie. When this instrument locks onto an object in space, it breaks down light into its component wavelengths with ruthless precision. Every element in the universe has a fingerprint, a unique signature written in the language of electromagnetic radiation. On that night in Chile, when the European Very Large Telescope's UV spectrograph focused on 3I/Atlas, it read a fingerprint that shouldn't exist. Let me take you inside that moment. Picture the Atacama Desert in Chile, one of the driest places on Earth. Here, where the air is so clear and stable that astronomers can peer deeper into space than almost anywhere else, sits the Very Large Telescope. 4 massive mirrors, each 8.2 meters across, working in concert to capture light that has traveled for years, decades, sometimes millions of years to reach us. The UV spectrograph is connected to one of these mirrors, and it's not just any spectrograph. This is one of the most sophisticated instruments ever built for analyzing the chemical composition of distant objects. When astronomers want to know what something in space is made of, UVs is their microscope, their chemical detective. On those nights in late 2024, UVs was trained on a point of light moving slowly against the background stars. To most people, 3I/Atlas would have looked like nothing special, just another faint dot in the cosmic haystack. But UVs sees beyond the visible. It takes that faint light and spreads it across thousands of individual wavelengths, creating a spectrum that reveals the atomic composition of whatever is producing that light. What it found changed everything. The first hint that something was wrong came when the data started flowing in. Dr. Elisa Fratin and her international team of researchers were expecting to see the usual suspects: carbon, oxygen, maybe some sodium, perhaps traces of other common elements that sublimate from comets as they approach the sun. These are the building blocks of cosmic ice and dust, the materials that formed in the cold outer regions of star systems billions of years ago. Instead, they saw lines that made no sense. Nickel. Strong, unmistakable nickel absorption lines dominated the spectrum. Not the faint traces you might occasionally see in unusual comets, but abundant, consistent signatures that indicated this object was producing nickel atoms at an extraordinary rate. Here's what you need to understand about spectroscopy. It's not guesswork. It's not interpretation. When UVs detects nickel, it's because nickel atoms in the comet's coma are absorbing specific wavelengths of sunlight and re-emitting them in characteristic patterns. These patterns are as unique as a human fingerprint, and they're consistent across the entire universe. Nickel on Earth produces the same spectral lines as nickel in the Andromeda Galaxy, but nickel shouldn't be there. Not in those quantities, not at those distances from the sun. The temperature required to sublimate nickel from rocky or metallic grains is enormous. We're talking about conditions that exist near the surfaces of stars, not in the cold vacuum of space where comets spend most of their time. At 3.14 astronomical units from the sun, where UVS first detected these signatures, the temperature is far too low for any natural process to vaporize nickel-bearing minerals. Yet there it was, night after night, observation after observation. The team conducted 6 separate observation sessions as 3I/ATLAS moved from 3.14 to 2.14 astronomical units from the sun. Each time, the spectrograph locked onto the comet and analyzed the light coming from its growing coma. Each time, nickel dominated the readings. The consistency was unprecedented. This wasn't a fluke or a measurement error. This was systematic, repeatable, and completely inexplicable. But here's where the story gets even stranger. As the comet moved closer to the sun, the team expected to see iron alongside the nickel. In natural stellar and planetary formation processes, nickel and iron are intimately linked. They form together, condense together, and when they sublimate, they typically appear together in predictable ratios. That's not what happened with 3I/Atlas. Iron remained absent from the spectra until the comet reached 2.64 astronomical units from the Sun. Only then did iron lines begin to appear, and even then, the ratio between nickel and iron was unlike anything in the scientific literature. The nickel to iron abundance ratio was not just unusual, it was impossible according to current models of comet formation and chemistry. Dr. Fratin and her colleagues documented this anomaly with the careful precision that characterizes modern astronomy. They cross-checked their measurements, verified their calibrations, and compared their results to decades of previous observations. The conclusion was unavoidable. 3I/Atlas was exhibiting extreme properties that had never been observed in any comet anywhere. The implications started to sink in as the team analyzed their data. This wasn't just an unusual comet. This was an object that challenged fundamental assumptions about how materials behave in interstellar space. The production rate of nickel atoms was so high that it suggested either the comet's surface was rich in easily vaporized nickel-bearing compounds, or something else entirely was happening. Traditional comet chemistry follows predictable patterns. As a comet approaches the Sun, ice begins to sublimate first, followed by more volatile compounds, and finally, at much closer distances and higher temperatures, rocky and metallic materials begin to outgas. The sequence is well understood and has been observed in hundreds of comets over decades of study. 3I/Atlas broke this pattern. It was producing metals at distances where ice should barely be active. It was generating chemical signatures that belonged to much hotter environments. It was behaving as if it were composed of materials that could sublimate easily, releasing nickel atoms into space at temperatures far too low for conventional nickel-bearing minerals. The research team faced a dilemma that every scientist fears: data that doesn't fit existing models. They could dismiss it as instrumental error, but UVES is one of the most reliable and well-calibrated instruments in astronomy. They could assume their analysis was flawed, but multiple independent checks confirmed their results, or they could accept that they were looking at something genuinely unprecedented. They chose the third option, and in doing so, they opened a door to questions that make the astronomical community uncomfortable. The paper they published used careful, measured language. They described the observations as extremely puzzling and noted that the presence of nickel and iron atoms in the comet's coma contradicted basic physics. They acknowledged that their findings represented extreme properties, unlike anything previously documented. But between the lines of scientific restraint, a more unsettling possibility emerged. What if 3I/Atlas isn't behaving like a typical comet because it isn't a typical comet? The spectroscopic evidence suggests an object with surface materials that can easily release nickel atoms at low temperatures. In terrestrial industry, such materials exist. Nickel carbonyl compounds, for instance, can sublimate at relatively low temperatures, releasing pure nickel atoms. These compounds are used in refining processes and specialized manufacturing applications. But nickel carbonyl doesn't occur naturally in space. It's a product of industrial chemistry, created through specific processes that require controlled environments and deliberate engineering. The UV spectrograph had detected something that looked remarkably like the signature of processed materials that had been refined, purified, and engineered for specific purposes. The kind of materials you'd expect to find in the wreckage of advanced technology, not in a primitive comet from another star system. This is where the discovery becomes more than just an astronomical curiosity. The implications extend beyond planetary science into questions about the prevalence of advanced civilizations in our galaxy. If 3I/Atlas represents processed materials, if it's carrying the chemical signature of industrial activity from another star system, then we're not just looking at an unusual comet. We're looking at archaeology. Interstellar archaeology. The UV spectrograph had done its job with mechanical precision. It had analyzed the light, identified the elements, measured the abundances, and documented the impossible. Now it was up to human intelligence to interpret what the machine had found. As the data circulated through the international astronomy community, reactions ranged from cautious interest to profound unease. Some researchers focused on finding natural explanations, proposing exotic formation scenarios or unknown chemical processes that might account for the observations. Others quietly acknowledged that the simplest explanation for the spectroscopic evidence was also the most disturbing. The machine had found something that looked artificial. 3. Nickel without iron. Here's what keeps me up at night about 3I/ATLAS. In 6 separate observations spanning months of careful study, nickel appeared every single time. Iron showed up fashionably late, only after the comet had moved significantly closer to the Sun. This isn't how chemistry works. This isn't how stellar formation works. This isn't how anything in nature works. Let me walk you through what this means, because the implications are staggering. When stars form, when planets condense, when comets accrete in the cold outer regions of solar systems, nickel and iron are chemical partners. They're part of the same processes, created in the same stellar furnaces, condensed under the same conditions. In every natural environment we've ever studied, from meteorites to planetary cores to interstellar dust grains, nickel and iron appear together in predictable ratios. Not with 3I/ATLAS. The UV spectrograph detected abundant nickel at 3.14 astronomical units from the Sun. At 2.94 AU, nickel was still there, still dominant. At 2.64 AU, nickel continued to flood the readings. But iron? Iron remained conspicuously absent until the comet reached that critical 2.64 AU threshold. Think about what this means. For months, as 3I/ATLAS moved through space, something on its surface was consistently releasing nickel atoms while keeping iron locked away. The temperatures weren't dramatically different across this range. The solar radiation intensity changed gradually. Yet the chemistry switched like someone had flipped a switch. This pattern doesn't exist in nature, but it does exist in something else. Something that makes the astronomical community profoundly uncomfortable. Industrial processes. When humans refine metals, when we create specialized alloys, when we engineer materials for specific purposes, we routinely separate nickel from iron. We create nickel-rich surfaces. We manufacture compounds that release pure nickel under controlled conditions. We design materials where nickel and iron sublimate at different temperatures, different pressures, different environments. The nickel to iron ratio in 3I/ATLAS doesn't just deviate from natural patterns, it mirrors artificial ones. Dr. Elisa Fratton's team documented this anomaly with painstaking precision. They measured the abundance ratios across all 6 observation periods. They compared their results to every known comet, every studied meteorite, every natural object in the solar system. The conclusion was inescapable. 3I/ATLAS was producing metal signatures unlike anything in the natural world. But here's where the story gets even more disturbing. The team didn't just compare 3I/ATLAS to objects in our solar system. They also compared it to 2I/Borisov, the previous interstellar comet that visited us in 2019. Borisov did show some traces of nickel, which was unusual but not unprecedented. What made 3I/ATLAS different was the sheer abundance and the delayed appearance of iron. Borisov's metal content, while noteworthy, followed patterns that could be explained by natural formation processes in another star system. Maybe that system had different chemical abundances. Maybe the comet formed in a region rich in nickel-bearing dust. The readings were unusual but not impossible. 3I/ATLAS crossed the line from unusual to impossible. The production rate of nickel atoms was so high that it suggested the comet's surface was essentially bleeding metal into space. This wasn't the gradual sublimation you'd expect from rocky grains embedded in ice. This was systematic, efficient, almost engineered release of specific elements under specific conditions. When I first read about these observations, I thought there had to be a simple explanation. Maybe the iron was there but somehow masked by other spectral lines. Maybe the measurement techniques weren't sensitive enough to detect iron at greater distances. Maybe there was some exotic chemistry at work that we simply didn't understand yet. Then I talked to spectroscopists, people who spend their careers analyzing light from distant objects, people who understand the capabilities and limitations of instruments like UVs. They all said the same thing. The iron should have been there. If natural processes were responsible for the nickel, iron should have appeared alongside it, not months later. The delayed appearance of iron suggests something even more disturbing than unusual chemistry. It suggests selectivity. It suggests that whatever process was releasing nickel from the comet's surface was specifically designed to release nickel first, iron later, under different conditions. This is exactly what you'd expect from engineered materials. Consider the industrial production of pure nickel. One common method involves creating nickel carbonyl compounds, which can be sublimated at relatively low temperatures to produce pure nickel vapor. The process is precise, controllable, and highly selective. It's used in manufacturing, in coating processes, in the production of specialized alloys. Nickel carbonyl doesn't occur naturally in space. It's a product of deliberate chemistry, created through specific reactions under controlled conditions. Yet the spectroscopic signature of 3I/ATUS looks remarkably similar to what you'd expect from materials rich in such compounds. The timing of iron's appearance adds another layer to the mystery. Iron began showing up in the spectra only after the comet had reached 2.64 AU from the Sun. At this distance, the temperature and radiation environment changed enough to trigger the release of different materials. Materials that had been stable at greater distances but began to outgas as conditions intensified. This sequential release of different metals suggests layered composition. It suggests that 3I/ATELAs might have surface materials designed to respond to different environmental conditions. First, easily sublimated nickel compounds responding to moderate heating. Later, more robust iron-bearing materials responding to increased temperature and radiation. Layered, responsive, sequential chemistry. This is the hallmark of engineered systems, not natural objects. The astronomical community has been remarkably restrained in discussing these implications. The published papers use careful language, focusing on the observational data rather than speculating about origins. But in private conversations, in conference hallways, in late-night discussions between researchers, a different conversation is happening. Some astronomers are quietly acknowledging that the simplest explanation for the nickel-iron separation is artificial origin. The chemistry looks engineered. The timing looks controlled. The abundance ratios look processed. But if that's true, then 3I/ATELAS isn't just an interstellar comet. It's an interstellar artifact, a piece of advanced technology that has somehow survived the journey between star systems and arrived here just as humanity developed the instruments to analyze it properly. The implications are staggering. We're not just talking about life existing elsewhere in the galaxy. We're talking about advanced technological civilizations that existed long enough and developed sophisticated enough capabilities to create materials that could survive interstellar travel. And now one of their artifacts is here, in our solar system, revealing its secrets to our spectrographs. The nickel without iron isn't just a chemical anomaly. It's potentially the first direct evidence of alien technology, not radio signals from space, not ambiguous formations on distant planets, not theoretical calculations about the possibility of life elsewhere. Physical evidence, chemical signatures, measurable, repeatable, undeniable data that suggests we are not alone. The UV's spectrograph didn't just detect nickel in the coma of 3I/ATLAS. It detected the possibility that somewhere, somewhen, In the vast reaches of interstellar space, intelligence arose that was capable of creating materials we're only now advanced enough to recognize. The question now isn't whether this chemistry is natural or artificial. The question is whether we're ready to accept what the evidence is telling us. 5 kilometers across. Let that sink in for a moment. 5 kilometers of dense material racing through space at speeds that dwarf anything we've ever built. To put this in perspective, imagine Manhattan Island, all of it, suddenly appearing in the outer solar system with a glowing tail of vaporized metals streaming behind it. That's 3I/AT, alas. That's what we're dealing with. But here's what should make you pause. This isn't just big, it's impossibly massive. Current estimates place its total mass at approximately 33 billion tons. 33 billion tons of material that originated in another star system, traveled through the void of interstellar space for potentially millions of years, and arrived here precisely when humanity developed the technology to study it in detail. The coincidence alone should make us uncomfortable. When the first estimates of 3I/8 size came back from observational data, astronomers had to double-check their calculations. Interstellar visitors aren't supposed to be this massive. The previous objects we detected, 1I/Oumuamua and 2I/Borisov, were relatively small. Oumuamua was estimated at roughly 100 to 1,000 meters in length. Borisov was closer to a kilometer in diameter. Both were significant discoveries, but they were also manageable sizes, objects that fit within our understanding of what interstellar debris should look like. 3I/AT is different. It's not just an interstellar visitor, it's an interstellar giant. The implications of this size become apparent when you consider what it would take to create such an object. In our solar system, comets of this magnitude are rare and typically originate from the Oort cloud, that distant shell of icy material that surrounds our sun at distances of up to 50,000 astronomical units. These objects represent some of the most pristine material from the early solar system, accumulated over billions of years of gravitational interactions. But 3I/AT didn't form in our solar system. It formed somewhere else, under different conditions around a different star. The fact that it achieved such massive proportions suggests either an extremely rich source of material in its home system or something else entirely. Let me walk you through the physics of what we're looking at. A 5-kilometer object with this density contains more material than most mountains on Earth. If 3I/AT were to impact our planet, the energy release would be cataclysmic on a scale that dwarfs any natural disaster in recorded history. We're talking about an extinction-level event, the kind of impact that reshapes continents and alters the course of biological evolution. Fortunately, 3I/AT is following a trajectory that will take it safely past Earth. But the fact remains, this object represents a concentration of material and energy that could literally end civilizations. The size also raises questions about how such an object could maintain its structural integrity during interstellar travel. The journey between star systems subjects any material to extreme temperature variations, cosmic radiation, impacts from interstellar dust and debris, and gravitational stresses as it passes through different stellar environments. Most objects would be gradually eroded, fragmented, or completely destroyed during such a journey. Yet 3I/AT not only survived the trip, it remained largely intact and continues to exhibit the organized chemistry we've been discussing. This suggests either exceptional structural durability or something more deliberate. Consider what it would take to engineer an object capable of surviving interstellar travel while maintaining specific chemical properties. You'd need materials that could withstand extreme temperature cycling. You'd need structural designs that could handle the stresses of acceleration and deceleration as the object moved through different gravitational fields. You'd need surface compositions that could resist erosion while preserving the ability to release specific elements under controlled conditions. This is exactly what we appear to be seeing with 3I/AT. The mass distribution also tells us something important about the object's composition. Early spectroscopic analysis suggested that the metals we're detecting represent surface activity, not the bulk composition of the object. If nickel and iron represent only a small fraction of the total mass, then the core of 3I/ATA must be composed of something else, something denser, more stable, capable of holding such massive quantities of material together. This raises uncomfortable questions about what might be hiding beneath the metal-rich surface. Are we looking at a rocky core with an engineered metallic shell? Are we seeing a composite structure designed for specific purposes, or are we dealing with something even more exotic? A manufactured object disguised as a natural comet? The timing of 3I/AT-LAS's arrival adds another layer of significance to its massive scale. This object appeared in our solar system just as humanity reached a level of technological sophistication that allows us to analyze its composition in detail. The UV spectrograph, the Hubble Space Telescope, the Mars Reconnaissance Orbiter. These are all recent developments in our observational capacity. Just a few decades ago, we wouldn't have been able to detect the chemical anomalies that make this object so significant. It's as if 3I/AT-LAS arrived precisely when we became capable of understanding what it might represent. The sheer scale of the object also dwarfs anything we could currently create or launch. Our most ambitious space missions involve objects weighing thousands of tons at most. The International Space Station, one of humanity's most complex orbital constructions, masses roughly 450 tons. The largest rockets we've ever built can launch payloads of at most a few hundred tons to interplanetary trajectories. 3I/AT-LAS represents a concentration of organized material that exceeds our current industrial capacity by orders of magnitude. If this object is artificial, it suggests a level of technological capability that far surpasses anything in human experience. But the most disturbing aspect of 3I/AT-LAS's size isn't what it tells us about its origin. It's what it tells us about the implications of its discovery. An object this massive, carrying this much organized material, represents a significant investment of resources and energy. Natural processes might occasionally create such concentrations of material, but they wouldn't organize them in ways that produce the chemical signatures we've observed. If 3I/AT-LAS is artificial, it represents evidence of industrial capacity on a scale that dwarfs human civilization. We're not talking about a small probe or a piece of debris from some interstellar accident. We're talking about a project that required massive resources, advanced materials science, and engineering capabilities that could create objects capable of surviving interstellar journeys while maintaining their function. This suggests civilizations with lifespans measured in millions of years, industrial capabilities spanning solar systems, and technological sophistication that makes our current achievements look primitive by comparison. The heavy metal comet isn't just carrying unusual chemistry. It's carrying implications that challenge our fundamental assumptions about intelligence, technology, and our place in the cosmic hierarchy of civilizations. As 3I/AT-LAS continues its approach through our solar system, every measurement we take reveals something that pushes the boundaries of what we thought was possible. The size, the mass, the chemistry, the timing, each piece of evidence adds weight to possibilities that most of us aren't ready to contemplate. But the evidence doesn't care whether we're ready. The 5-kilometer giant is here. It's real. And it's forcing us to confront questions about the nature of intelligence in the universe that we've only begun to explore. 29 million kilometers. That's the distance at which 3I/AT-LAS will pass Mars, close enough for humanity's best orbital cameras to capture details that will either solve this mystery or deepen it beyond anything we've imagined. Right now, as this interstellar visitor approaches its closest encounter with the red planet, 3 sophisticated spacecraft are positioning themselves for what may be the most important observational event in the history of astronomy. NASA's Mars Reconnaissance Orbiter is ready. ESA's Mars Express mission stands by. The ExoMars Trace Gas Orbiter has aligned its instruments, Together, these three mechanical eyes represent humanity's best chance to look directly into the heart of an interstellar visitor and determine once and for all what we're really dealing with. The timing couldn't be more perfect or more unsettling. Consider what we're about to witness. The MRO's HiRISE camera, one of the most powerful imaging systems ever deployed in interplanetary space, will capture 3I/8LS at a resolution of approximately 30 kilometers per pixel. To put this in perspective, the best images we currently have were taken by Hubble from Earth when the comet was 570 million kilometers away. The Mars encounter will bring us 20 times closer, 20 times more detail, 20 times more opportunity to see what this object really is. But here's what makes this encounter so significant beyond just the improved resolution. Mars provides a unique vantage point that Earth-based telescopes simply cannot match. From Mars orbit, the three spacecraft will observe 3I/8LS under different lighting conditions, from multiple angles across different wavelengths of electromagnetic radiation. They'll capture not just visible light images but infrared signatures, thermal profiles, and spectroscopic data that could reveal structural details invisible from Earth. The HiRISE camera alone represents a technological marvel that makes this observation possible. Originally designed to study Martian surface features, HiRISE can resolve objects as small as 30 centimeters across when observing the planet's surface from its orbital altitude. Applied to 3I/8LS at its closest approach, this means we'll see details of the comet's nucleus with unprecedented clarity. What will those details reveal? The question keeps me awake at night. If 3I/8LS is a natural comet with unusual chemistry, the Mars encounter should show us a rocky, irregular surface with active sublimation regions producing the metal-rich plumes we've detected spectroscopically. We should see jets of material streaming away from the nucleus, creating the coma that UVs has been analyzing for months. We should see, in other words, exactly what we'd expect from any comet approaching the Sun. But what if we don't? The spectroscopic evidence we've already discussed, the nickel without iron, the impossible abundance ratios, the sequential chemistry that looks engineered rather than natural. All of this suggests we might see something very different when HiRISE focuses on the nucleus of 3I/8LS. Geometric structures, reflective surfaces, organized patterns that don't occur in natural objects. The thought is simultaneously thrilling and terrifying. Mars Express adds another dimension to the observation campaign. This veteran spacecraft, which has been studying Mars since 2003, carries instruments capable of detailed spectroscopic analysis. While HiRISE captures visual details, Mars Express can analyze the chemical composition of 3I/8LS from its unique vantage point, potentially revealing variations in surface materials that aren't detectable from Earth. The ExoMars Trace Gas Orbiter brings yet another perspective. Originally designed to study the Martian atmosphere, TGO's instruments can analyze the gas cloud surrounding 3I/8LS with sensitivity that far exceeds Earth-based capabilities. If this object is releasing processed materials into space, TGO should detect chemical signatures that tell us exactly what kinds of industrial processes might be involved. 3 spacecraft, multiple instruments, unprecedented resolution. This represents the most comprehensive observational campaign ever directed at an interstellar visitor. But there's something else that makes this encounter historically significant. The timing suggests that 3I/8LS's trajectory was either extraordinarily fortunate or carefully planned. Think about the odds. This object originated in another star system, traveled through interstellar space for potentially millions of years, and arrived in our solar system at precisely the moment when humanity had advanced spacecraft positioned around Mars with instruments capable of detailed analysis. The statistical probability of such a coincidence is astronomical, unless it's not a coincidence. The trajectory of 3I/8LS brings it close enough to Mars for detailed observation, but not so close as to be gravitationally captured or deflected significantly from its path. It's almost as if the approach was calculated to provide maximum observational opportunity while maintaining the object's integrity and trajectory. This raises questions that make the astronomical community profoundly uncomfortable. Are we witnessing a natural encounter with an unusual interstellar object, or are we being presented with an opportunity to observe something that wants to be observed? The Mars encounter will provide answers to some questions and probably raise many more. The images and data collected during this flyby will be analyzed for years, revealing details about 3I/Attilas that could reshape our understanding of interstellar objects, planetary formation, and the prevalence of advanced technology in the galaxy. But beyond the scientific implications, this encounter represents something more profound. It's humanity's first close-up examination of an object that may represent evidence of intelligence beyond Earth. The cameras and instruments positioned around Mars aren't just collecting astronomical data, they're potentially documenting first contact. The thought that we might be looking at the remnants of an advanced technological civilization from another star system should give us pause. The implications extend far beyond astronomy into questions of philosophy, sociology, and our fundamental understanding of our place in the universe. As the Mars encounter unfolds, we'll learn not just about the composition and structure of 3I/Atlas, but about our own readiness to confront evidence that we are not alone in the universe. The 3 spacecraft orbiting Mars carry more than just scientific instruments. They carry humanity's hopes, fears, and curiosity about what lies beyond our small corner of the cosmos. The data they collect in the coming days will either confirm that 3I/Attilas is an unusual but natural object, or it will force us to confront the possibility that we are looking at archaeology from another star system. Either way, the Mars encounter will be remembered as a turning point in human understanding of our cosmic neighborhood. The question is whether we're prepared for what that understanding might reveal. 6 separate opportunities to peer into the chemical soul of an interstellar visitor. 6 moments when the UVIS spectrograph captured light that had bounced off materials from another star system and revealed secrets that challenge everything we thought we knew about cosmic chemistry. Let me walk you through this data puzzle piece by piece, because the pattern that emerges is more disturbing than any single anomalous reading. The observations began when 3I/Attilas was 3.14 astronomical units from the Sun. At this distance, the object was receiving roughly 1/10 the solar radiation that Earth experiences. The temperatures were so low that conventional wisdom said no metals should be sublimating from its surface. Yet when UVIS analyzed the light coming from the comet's developing coma, nickel, abundant, unmistakable, impossible nickel. The second observation came at 2.94 AU, still cold, still well beyond the range where traditional comet chemistry should produce metal signatures. But nickel continued to dominate the spectrum. Not traces, not hints. Strong, consistent absorption lines that indicated the object was releasing nickel atoms at an extraordinary rate. By the third observation at 2.64 AU, something changed. This was the moment when iron finally appeared in the spectroscopic data. After months of nickel without iron, of chemistry that defied natural explanations, iron lines began to show up alongside the continued nickel signatures. But even then, the ratios were wrong. The abundance patterns looked nothing like what occurs in natural stellar formation processes. The 4th, 5th, and 6th observations, taken as 3I/Attilas, moved from 2.44 AU to 2.14 AU, revealed a chemistry that became increasingly complex but never became natural. The nickel to iron ratios remained stubbornly artificial looking. The production rates of both metals continued to exceed anything documented in solar system comets. But here's the part that should make you deeply uncomfortable. The pattern isn't random. It's not chaotic. It's not the kind of erratic chemistry you'd expect from a natural object responding unpredictably to changing solar radiation. The pattern is organized. Sequential, almost programmed. Think about what this means. As 3I/ATLAS moved closer to the Sun, different materials began to outgas at different distances. First, easily sublimated nickel compounds at greater distances. Then, more robust iron-bearing materials as conditions intensified. The timing was precise. The chemistry was layered. The response to environmental changes was sophisticated. This is exactly what you'd expect from engineered materials designed to respond predictably to changing conditions. Dr. Elisa Frattin's team documented this progression with meticulous care. They measured not just the presence of these metals, but their abundance ratios, production rates, and temporal variations. The data reveals an object that isn't just chemically unusual, it's chemically responsive. Natural comets don't behave this way. When ice sublimates from a comet's surface, it releases whatever materials were trapped within it in ratios that reflect the comet's formation environment. There might be some variation as different regions of the surface become active, but the overall chemistry remains relatively consistent. You don't see systematic changes in elemental ratios as a function of distance from the Sun. 3I/ATLAS shows exactly this kind of systematic behavior. The 6-interval progression reveals something that looks less like natural sublimation and more like controlled release, as if different layers of surface material were designed to activate at different temperatures, releasing specific elements in predetermined sequences. Consider the industrial implications of such behavior. If you wanted to create a material that could survive interstellar travel while preserving the ability to release specific chemicals under controlled conditions, you'd design layered surfaces. Easily activated outer materials for initial response to stellar heating. More robust inner materials for sustained release under increased radiation. Sequential chemistry designed to produce specific signatures at specific distances from a star. This is sophisticated materials engineering. This is technology. The consistency of the pattern across all 6 observations eliminates the possibility of measurement error or instrumental malfunction. UVS is one of the most reliable spectrographs in astronomy, with decades of calibration data and thousands of successful observations. When it detects nickel, it's because nickel is there. When it measures abundance ratios, those ratios are real. The pattern also eliminates natural explanations based on unusual formation environments. Even if 3I/ATLAS formed in a region of space with exotic chemistry, that chemistry would be reflected consistently across all observations. You wouldn't see the kind of systematic changes that characterize the 6-interval progression. What the data suggests instead is an object with multiple layers of engineered materials, each designed to respond to specific environmental conditions. This isn't just advanced chemistry, it's advanced materials science applied on an interstellar scale. The implications extend beyond the object itself to questions about the civilization that might have created it. The level of sophistication required to design materials that could maintain their properties during interstellar travel while producing specific chemical signatures under controlled conditions represents a technological capability that far exceeds current human achievements. We're talking about materials science that spans millions of years, engineering projects that account for the challenges of interstellar travel, industrial capabilities that can create objects capable of surviving the journey between star systems while maintaining their function. But perhaps the most disturbing aspect of the 6-interval progression is what it suggests about the purpose of 3I/ATLAS. Natural objects don't carry organized chemistry across interstellar distances. They don't maintain layered materials designed for sequential release. They don't exhibit controlled responses to environmental changes. Objects with these characteristics have purposes. They're designed to do something specific under specific conditions. The sequential chemistry we've observed could serve many purposes. Communication, leaving chemical signatures that advanced civilizations could detect and analyze. Exploration, gathering information about stellar environments and transmitting that information through chemical releases. Delivery, carrying specific materials to specific locations for specific reasons, or it could serve a purpose we haven't imagined yet, something that requires the kind of sophisticated materials engineering we've documented, but for reasons that won't become apparent until we learn more about what 3I/Étoiles really is. The 6 intervals of observation have given us a puzzle with pieces that don't fit together using natural explanations. The chemistry is too organized, the timing is too precise, the response to environmental changes is too sophisticated. We're left with data that points toward conclusions most of us aren't ready to accept. The evidence suggests we're looking at technology, advanced technology from another star system, technology that has traveled across interstellar space and arrived here precisely when humanity developed the instruments to recognize what it might represent. The 6 intervals haven't just documented unusual chemistry, they've documented the possibility that we are not alone in the universe, and that we now have physical evidence of intelligence beyond Earth floating in our solar system, waiting to be understood. 3 visitors from beyond our solar system, 3 opportunities to understand what kinds of objects travel through the vast emptiness between stars, 3 chances to learn whether we're alone in the universe or part of something much larger and more complex. Each visitor has been stranger than the last. 1I/Oumuamua arrived first in October 2017 and immediately challenged our assumptions about interstellar objects. Roughly 100 to 1,000 meters in length, cigar-shaped or pancake-flat, depending on which analysis you believed, Oumuamua exhibited behavior that defied explanation. It showed no signs of cometary activity despite its trajectory suggesting it should have developed a tail. As it approached the Sun, more disturbing, it exhibited unexplained acceleration as it left our solar system, acceleration that couldn't be accounted for by gravitational forces alone. The astronomy community struggled to explain Oumuamua's strange behavior. Some proposed that it was composed of hydrogen ice, which would sublimate invisibly and provide the thrust needed for the observed acceleration. Others suggested it might be a fragment of a larger object, broken off by tidal forces during a close encounter with another star. A few researchers, led by Avi Loeb, proposed that its unusual properties might indicate artificial origin, a piece of advanced technology from another civilization. The debate over Oumuamua continues to this day, but one thing became clear: interstellar visitors don't necessarily behave like objects from our own solar system. 2I/Borisov arrived in August 2019 and initially seemed to restore some normalcy to the concept of interstellar comets. Roughly 1 kilometer in diameter, Borisov developed a proper comet tail, exhibited predictable sublimation activity, and generally behaved like astronomers expected an interstellar comet to behave. It was composed of familiar materials, water ice, carbon monoxide, dust, in ratios that were unusual but not impossible to explain through natural formation processes. But even Borisov carried surprises. Spectroscopic analysis revealed traces of nickel in its coma, which was unusual but not unprecedented. Some solar system comets also show nickel signatures, though typically at much lower abundances. Borisov's nickel content was notable enough to warrant scientific papers, but it fell within the range of what could be explained by natural processes in an alien star system. Borisov also exhibited some structural peculiarities. Its nucleus appeared to be unusually fragmented, possibly indicating that it had undergone significant stress during its interstellar journey. Some observations suggested it might be shedding material more rapidly than expected, though this could be explained by its unfamiliar chemical composition or structural weaknesses developed during eons of cosmic travel. Overall, Borisov was weird but comprehensible. It expanded our understanding of interstellar chemistry without fundamentally challenging our models of how such objects should behave. Then came 3I/Étoiles. If Oumuamua was strange and Borisov was unusual, 3I/Atlas is impossible. Everything about this object violates our understanding of natural chemistry, stellar formation processes, and interstellar physics. The size comparison alone is staggering. Oumuamua was measured in hundreds of meters. Borisov was roughly a kilometer across. 3I/Atlas spans 5 kilometers and contains an estimated 33 billion tons of material. It's not just bigger than its predecessors, it's orders of magnitude more massive than anything we expected to find traveling between star systems. But size is just the beginning of the differences. The chemistry of 3I/Atlas dwarfs the anomalies observed in previous visitors. Borisov's nickel traces were noteworthy. 3I/Atlas is practically bleeding nickel into space at rates that exceed any natural explanation. The production rates are so high that they suggest surface materials specifically designed to release metals under stellar heating. The nickel-to-iron ratios tell an even more disturbing story. Borisov's metal content, while unusual, could be explained by formation in a star system with different chemical abundances than our own. 3I/Atlas exhibits ratios that don't occur anywhere in nature. Ratios that look industrial, processed, engineered. The temporal patterns add another layer of impossibility. Borisov's chemistry remained relatively stable throughout its passage through our solar system. 3I/Atlas shows systematic changes in elemental release as a function of distance from the Sun. Nickel appears first, iron appears later. Abundance ratios shift in organized patterns that suggest layered surface materials responding to changing environmental conditions. This kind of responsive chemistry doesn't exist in natural objects. It's the hallmark of engineered systems designed to perform specific functions under controlled conditions. The trajectory comparisons reveal yet another anomaly. Oumuamua followed a hyperbolic path that took it quickly through our solar system and back into interstellar space. Borisov had a more leisurely trajectory that allowed extended observation but still carried it away from our solar system in a reasonable time frame. 3I/Atlas is following a path that brings it close enough to Mars for detailed observation, almost as if the trajectory were calculated to maximize observational opportunities. The timing of each visit also deserves consideration. Oumuamua arrived just as humanity was developing the observational capabilities needed to detect and track interstellar objects. Borisov appeared as our spectroscopic instruments reached the sensitivity required to analyze interstellar chemistry. 3I/Atlas has arrived precisely when our Mars-orbiting spacecraft can provide unprecedented close-up observations of an interstellar visitor. Either we're experiencing a remarkable series of coincidences, or these visits are timed to coincide with our developing technological capabilities. The progression from Oumuamua to Borisov to 3I/Atlas suggests a pattern that makes the astronomical community uncomfortable. Each visitor is stranger than the last. Each pushes the boundaries of natural explanation further than the previous one. Each arrives with properties that challenge our fundamental assumptions about what kinds of objects should exist in interstellar space. Oumuamua might have been a natural object with unusual properties. Borisov was probably a normal interstellar comet with interesting chemistry. But 3I/Atlas crosses the line from unusual to impossible, from interesting to alarming, from natural to potentially artificial. The comparison forces us to confront questions about the nature of interstellar space that we've avoided until now. Is the galaxy filled with natural debris from stellar formation processes, or is it populated by artifacts from advanced civilizations, technological remnants that occasionally wander into our solar system and reveal themselves to our increasingly sophisticated instruments? The three visitors tell a story of escalating strangeness that points toward conclusions most of us aren't ready to accept. But the evidence doesn't care about our readiness. Each interstellar visitor has been more impossible than the last. Each has carried chemistry, physics, or behavior that challenges our understanding of what should exist in the space between stars. 3I/Atlas represents the culmination of this progression. It's not just another strange interstellar object. It's an object so strange, so chemically impossible, so structurally sophisticated, that it forces us to consider explanations that go beyond natural formation processes. The visitors from beyond our solar system haven't just expanded our understanding of interstellar objects. They've opened the door to possibilities that could fundamentally change our understanding of intelligence, technology, and life in the universe. 4 possibilities. 4 attempts to explain the impossible chemistry of 3I/ATLAS using the tools of science, logic, and increasingly uncomfortable speculation. Each theory represents a different challenge to our understanding of what should exist in interstellar space, and each leads us deeper into questions that make the astronomical community profoundly uneasy. Let me walk you through each possibility like a detective, examining evidence at a crime scene, because that's what this feels like. A cosmic crime scene where the laws of natural chemistry have been violated, and we're trying to determine whether we're looking at an accident of nature or something far more deliberate. Theory 1: fragment of a metallic planetary core. The most conservative explanation suggests that 3I/ATLAS is a fragment of a metallic planetary core, blasted free from its home system by some catastrophic event. Perhaps a supernova destroyed a nearby planet, or a stellar collision shattered entire worlds, sending pieces of their metallic cores racing through interstellar space. This theory would explain the high metal content. Planetary cores are rich in iron and nickel, formed through billions of years of gravitational differentiation, as heavy elements sink toward the center of forming worlds. If 3I/ATLAS originated from such a core, it would naturally contain the metals we're detecting. But the theory breaks down when we examine the details. Planetary cores don't exhibit the layered chemistry we've observed. They don't release nickel first and iron later in organized sequences. They don't show abundance ratios that change systematically with distance from a star. Natural planetary materials respond to heating in predictable ways, releasing their constituent elements in ratios that reflect their formation environment. 3I/ATLAS doesn't behave like any natural planetary material we've ever studied. Theory 2: exotic chemical processes. Perhaps there are chemical processes at work in other star systems that don't exist in our own. Maybe 3I/ATLAS formed in an environment with exotic chemistry, unusual stellar compositions, or formation processes that produced materials with properties we've never encountered. This theory appeals to our natural assumption that the universe is stranger than we currently understand. There are certainly chemical processes occurring around other stars that don't happen in our solar system. Different stellar masses, compositions, and evolutionary stages could produce materials with unusual properties, but even exotic chemistry follows predictable rules. Elements don't violate their fundamental properties just because they formed around different stars. Nickel and iron should still appear together in natural processes. Sequential release of different metals should still require systematic heating or chemical changes that we're not observing in 3I/ATLAS's environment. The exotic chemistry theory requires us to invent entirely new chemical processes that have never been observed anywhere in the universe. It asks us to believe that natural law works differently in other star systems in ways that produce effects indistinguishable from advanced technology. Theory 3: extreme comet activity. Maybe 3I/ATLAS is just an unusual comet exhibiting extreme activity triggered by solar heating. Perhaps its surface materials are more volatile than typical comets, or its internal structure creates heating patterns that produce the organized chemistry we've observed. This theory tries to keep 3I/ATLAS within the realm of natural objects while accounting for its unusual behavior. Comets are notoriously unpredictable, and we're still learning about the variety of chemistry and structure that can exist in these ancient objects. But the extreme activity theory fails to explain the systematic nature of what we're observing. Extreme comet activity might produce high metal content, but it wouldn't produce the layered sequential chemistry that characterizes 3I/ATLAS. Natural sublimation processes don't create the kind of organized temporal patterns we've documented across 6 separate observation intervals. The theory also fails to explain the impossible nickel-to-iron ratios. even extreme activity can't change the fundamental chemistry of the materials involved. If 3I/Atlas were a natural comet, its metal content should reflect natural formation processes, regardless of how vigorously it's outgassing. Theory 4. Artificial origin. This is the theory that keeps astronomers awake at night. The possibility that 3I/Atlas isn't natural at all, but rather the remnant of advanced technology from another star system, an artifact that has survived interstellar travel and arrived here carrying evidence of intelligence beyond Earth. Avi Loeb has been the most prominent advocate of considering artificial explanations for unusual astronomical objects. His analysis of Oumuamua led him to propose that its strange properties might indicate technological origin. With 3I/Atlas, the evidence is even more compelling. The nickel without iron chemistry looks exactly like what you'd expect from industrial processes. The sequential release of different metals suggests layered materials designed to respond to changing environmental conditions. The abundance ratios mirror artificial alloys rather than natural stellar formation. The artificial origin theory explains all the anomalies that puzzle other explanations. The organized chemistry makes sense if the materials were engineered. The sequential behavior makes sense if different layers were designed for different purposes. The impossible ratios make sense if the materials were processed rather than naturally formed. But this theory carries implications that extend far beyond astronomy. If 3I/Atlas is artificial, it represents evidence of advanced technological civilization capable of creating objects that could survive interstellar travel. We're not just talking about the existence of life elsewhere in the galaxy. We're talking about intelligence sophisticated enough to engineer materials that we're only now advanced enough to recognize. The artificial origin theory forces us to confront questions about our place in the cosmic hierarchy of civilizations. Are we alone? Are we primitive by galactic standards? Are we being observed, studied, contacted in ways we're only beginning to understand? Each theory represents a different challenge to our worldview. The planetary core fragment theory requires us to accept that natural objects can exhibit impossible chemistry. The exotic chemical processes theory requires us to believe that fundamental physical laws work differently elsewhere in the universe. The extreme comet activity theory requires us to ignore systematic patterns that contradict natural explanations. Only the artificial origin theory provides explanations that are consistent with all the observed evidence. But it's also the theory that carries the most profound implications for humanity's understanding of our place in the universe. The evidence doesn't care about our comfort level. The chemistry of 3I/Atlas looks artificial. The behavior looks engineered. The timing looks deliberate. The sequential patterns look designed. We're left with a choice between natural explanations that don't fit the evidence and artificial explanations that challenge our fundamental assumptions about intelligence in the universe. The theories are on the table. The evidence continues to accumulate. The question is whether we're prepared to follow that evidence wherever it leads, even if it leads us to conclusions that fundamentally change our understanding of what exists in the space between stars. Avi Loeb doesn't mince words. When one of the world's most respected theoretical physicists looks at the chemistry of 3I/Atlas and states flatly that the detection of nickel without iron is only known to exist in industrially produced alloys made through the artificial carbonyl chemical pathway, the implications should make us pause and perhaps tremble. This isn't speculation from the fringe of science. This is analysis from the former chair of Harvard's astronomy department, a scientist who has published over 800 papers in peer-reviewed journals, someone whose work has shaped our understanding of black holes, cosmic gamma-ray bursts, and the early universe. When Avi Loeb suggests that an astronomical object might be artificial, the scientific community listens, even when they don't want to hear what he's saying. The carbonyl chemical pathway that Loeb references is a sophisticated industrial process used to refine and purify metals. It involves creating volatile metal compounds that can be easily manipulated, transported, and processed under controlled conditions. In human industry, this pathway is used to produce pure nickel for specialized applications: electronics, catalysts, precision alloys that require specific properties. The key characteristic of this process is that it produces pure nickel without the ion contamination that typically accompanies nickel in natural formations. When nickel and iron form together in stellar environments, they're intimately mixed at the atomic level. Separating them requires deliberate chemistry, controlled environments, and sophisticated understanding of metallurgical processes. Nature doesn't perform nickel-ion separation, industry does. The spectroscopic signature of 3I/ATLAS shows exactly this kind of separation: abundant nickel without corresponding iron, released under conditions that suggest controlled sublimation rather than natural outgassing. The chemistry looks processed, refined, engineered, but Loeb's analysis goes deeper than just the carbonyl pathway. He notes that the high nickel production rate combined with the unusual nickel-to-iron ratio makes 3I/ATLAS exceptional when compared to any natural object we've ever studied. Not unusual, not rare, exceptional, meaning it falls outside the range of what natural processes should be able to produce. This assessment comes from someone who has spent decades studying exotic astrophysical phenomena: black holes, neutron stars, gamma-ray bursts, the most extreme environments in the universe. Yet the chemistry of 3I/ATLAS stands out as exceptional even in the context of cosmic extremes. The implications of Loeb's analysis extend far beyond the simple presence of industrial chemistry in an interstellar object. If 3I/ATLAS represents processed materials, if it carries the signature of advanced metallurgy, then we're looking at evidence of technological civilization capable of creating objects that could survive interstellar travel while maintaining their engineered properties. This isn't just advanced chemistry. This is materials science applied on an interstellar scale. It suggests civilizations with industrial capabilities that span solar systems, technological lifespans measured in millions of years, and engineering sophistication that makes our current achievements look primitive by comparison. But the most disturbing aspect of Loeb's analysis isn't what it tells us about the object itself, it's what it tells us about the timing of its discovery. Advanced industrial artifacts don't just randomly appear in solar systems, they're created for purposes. They're sent with intentions. They arrive when they're supposed to arrive. 3I/ATLAS appeared in our solar system precisely when humanity developed the spectroscopic capabilities needed to recognize industrial chemistry in space. The UVIS spectrograph that detected the impossible nickel signatures has only existed for a few decades. The analytical techniques needed to identify artificial chemical processes in astronomical objects are even more recent. It's as if this artifact waited for us to become sophisticated enough to understand what we were looking at. The artificial origin hypothesis also explains other anomalies that natural theories struggle with. The massive size of 3I/ATLAS makes sense if it's an engineered object designed for long-term interstellar travel. The layered chemistry makes sense if different surface materials were designed to respond to different environmental conditions. The sequential release of metals makes sense if the object was programmed to reveal specific information under specific circumstances. But accepting Loeb's analysis requires us to confront implications that extend far beyond astronomy. If 3I/ATLAS is artificial, it represents physical evidence that we are not alone in the universe. Not radio signals, not ambiguous formations on distant planets, not theoretical calculations about the probability of life. Chemical signatures, measurable data that we can hold in our instruments and analyze in our laboratories. The exotic possibility forces us to ask questions that most of humanity isn't ready to contemplate. Who created this object? When? Why? What were they trying to accomplish by sending processed materials across interstellar space? Are they still active? Still monitoring? still capable of creating objects like 3I/8LS? And perhaps most importantly, are there more of these artifacts in our solar system? Are we surrounded by evidence of advanced technological civilizations that we've been too primitive to recognize until now? Loeb's analysis suggests that the universe might be filled with technological debris from civilizations that rose and fell long before our sun even formed. Ancient artifacts drifting through space, carrying chemical signatures that reveal their artificial origins to any species advanced enough to build the right instruments. This possibility transforms our understanding of interstellar space from a vast emptiness punctuated by natural objects to a cosmic archaeology site filled with the remnants of intelligence that preceded us by eons. Every unusual object that enters our solar system becomes a potential artifact. Every anomalous chemistry reading becomes a possible signature of technology. The exotic possibility also raises questions about contact, communication, and the intentions of civilizations capable of creating objects like 3I/Atlas. Are these artifacts meant to be found? Are they carrying messages, information, or technology that we're supposed to discover when we become advanced enough to recognize them? Or are they simply the inevitable debris of civilizations that span galactic distances? The industrial waste of intelligence is so advanced that they casually create objects capable of interstellar travel without considering that primitive species like ourselves might eventually encounter them. R.V. Loeb's analysis of 3I/RLS doesn't just suggest that this object might be artificial. It suggests that artificial objects might be common in interstellar space, that we've entered a phase of technological development where we can begin to recognize the signatures of intelligence that has been surrounding us all along. The exotic possibility isn't just about one unusual comet. It's about the transformation of human understanding from a species that assumes it's alone in the universe to a species that recognizes it's part of a galaxy filled with evidence of intelligence. Intelligence that we're finally advanced enough to detect, analyze, and perhaps someday understand. The question isn't whether 3I/8LS is natural or artificial. The question is whether we're ready to accept what the evidence is telling us about our place in a universe that might be far more populated, far more technologically sophisticated, and far more interconnected than we ever imagined. This isn't just about one interstellar comet carrying unusual chemistry. This is about the fundamental question of whether we are alone in the universe and the possibility that we're about to discover we never were. 3I/Atlas represents something far more significant than an astronomical curiosity. It's potentially the first direct physical evidence of intelligence beyond Earth. Not radio signals that could be natural phenomena, not ambiguous structures on distant planets that could be geological formations, not theoretical calculations about the probability of life elsewhere in the galaxy, physical evidence. Chemical signatures that we can measure, analyze, and verify using the most sophisticated instruments humanity has ever built. If the artificial origin hypothesis is correct, if 3I/Atlas truly represents processed materials from an advanced technological civilization, then we're not just witnessing an unusual astronomical event. We're documenting first contact. We're analyzing artifacts from beings who achieved interstellar travel capability long before our species even existed. The implications cascade through every aspect of human understanding: philosophy, religion, science, technology, social structures. Everything we thought we knew about our place in the cosmic hierarchy would need to be reconsidered. Consider what it means if advanced technological civilizations are common enough in our galaxy that their artifacts occasionally wander into our solar system. The statistical implications are staggering. If 3I/Atlas is artificial, it suggests that interstellar space is littered with the remnants of intelligence, that technological civilizations have been creating objects capable of surviving interstellar travel for millions or billions of years. We wouldn't be discovering the first evidence of extraterrestrial intelligence. We'd be discovering that we've been surrounded by such evidence all along, but we were too primitive to recognize it. The timing of this discovery adds another layer of significance. Humanity has existed in its current form for roughly 200,000 years. We've had writing for maybe 5,000 years. We've had the scientific method for a few centuries. We've had the technology to detect and analyze interstellar objects for less than a human lifetime. Yet within this tiny window of technological capability, we've encountered 3 interstellar visitors, each stranger than the last, culminating in an object that exhibits chemistry indistinguishable from advanced industrial processes. Either we're experiencing the most remarkable coincidence in the history of science, or these encounters are not coincidental. The objects might be arriving precisely when we've developed the capability to recognize what they represent. They might be part of a process, a revelation, a disclosure that operates on timescales far longer than human civilization. The biggest stakes involve more than just confirming that we're not alone. They involve understanding our relationship to intelligences that preceded us by potentially millions of years. Civilizations that achieve technological capabilities we can barely imagine. Species that solved the challenges of interstellar travel, materials science, and long-term engineering projects that span galactic distances. If 3i/Atlas is artificial, we're not just discovering that extraterrestrial intelligence exists. We're discovering that it exists at a level of sophistication that dwarfs human achievement by orders of magnitude. This realization should humble us. The chemistry we're detecting in 3i/Atlas represents materials science beyond our current capabilities. The engineering required to create objects that could survive interstellar travel while maintaining their properties represents project management on scales we've never attempted. The industrial capacity needed to create 33 billion-ton artifacts represents resource utilization that exceeds human civilization's total historical output. We're potentially looking at evidence of civilizations that treat interstellar engineering the way we treat intercity transportation, species for which creating objects like 3i/Atlas is routine industrial activity rather than the ultimate technological achievement. But the bigger stakes also involve opportunity. If advanced technological civilizations are common in our galaxy, if they leave artifacts that we can detect and analyze, if they're sophisticated enough to time the arrival of such artifacts to coincide with our developing observational capabilities, then we might be on the verge of the greatest learning opportunity in human history. Every unusual object that enters our solar system becomes a potential classroom. Every anomalous chemistry reading becomes a possible lesson in advanced materials science. Every artifact we identify becomes a window into technological capabilities that could accelerate human development by centuries or millennia. The analysis of 3i/Atlas isn't just revealing the composition of an interstellar visitor, it's potentially revealing industrial processes that we haven't invented yet. Chemical techniques that could revolutionize our materials science, engineering approaches that could solve fundamental challenges in space exploration, energy production, and resource utilization. But accessing these opportunities requires us to acknowledge what we're looking at. It requires us to move beyond comfortable assumptions about our uniqueness in the universe and accept that we might be students rather than pioneers in the development of interstellar capabilities. The bigger stakes involve the transformation of human civilization from a species that assumes it's alone to a species that recognizes it's part of a galactic community of intelligence. This transformation carries risks as well as opportunities. How do we maintain human agency and cultural identity while acknowledging that we're technological infants compared to civilizations capable of creating objects like 3i/Atlas? How do we navigate the psychological and social implications of discovering that everything we've achieved represents a tiny fraction of what's possible? How do we proceed with our own technological development while potentially having access to evidence of far more advanced approaches? These questions don't have easy answers, but they're questions we may need to answer sooner than we anticipated. The evidence continues to accumulate. The chemistry of 3i/Atlas continues to point toward artificial origin. The implications continue to expand beyond astronomy into fundamental questions about intelligence, technology, and humanity's future. The biggest stakes aren't just about one interstellar comet, they're about the possibility that we're living through the most significant moment in human history. The moment when we discovered that we are not alone, that we have never been alone, and that the universe is far more interesting, far more populated, and far more technologically sophisticated than we ever dared to imagine. Whether we're ready for these discoveries is irrelevant. The evidence doesn't care about our readiness. 3I/ATLAS is here. Its chemistry is impossible to explain through natural processes. Its implications continue to point toward conclusions that will fundamentally change our understanding of our place in the cosmic community of intelligence. The question isn't whether we're ready for this transformation. The question is how we'll respond when the evidence becomes too overwhelming to ignore. In the next few days, 3 mechanical eyes orbiting Mars will capture images that could answer the most profound question in human history. Are we alone in the universe? The Mars Reconnaissance Orbiter's high-rise camera stands ready. ESA's Mars Express mission has positioned its instruments. The ExoMars Trace Gas Orbiter has aligned its sophisticated sensors. Together, they represent humanity's best chance to peer directly into the heart of an interstellar visitor and determine once and for all whether we're looking at chemistry or technology. The anticipation is electric among astronomers worldwide. After months of analyzing spectroscopic data that defies natural explanation, after documenting chemistry that looks industrial rather than cosmic, after measuring abundance ratios that mirror artificial processes, we're finally going to see what 3I/ATLAS actually looks like. But here's what makes this moment so nerve-wracking. The images we're about to receive will either resolve the mystery by showing us a mundane rocky object with unusual surface chemistry, or they'll deepen it by revealing structures, patterns, or features that no natural comet should possess. The high-rise camera represents the pinnacle of interplanetary imaging technology. Originally designed to study Martian geology from orbit, this instrument can resolve details as small as 30 centimeters when observing Mars from its operational altitude. Applied to 3I/ATLAS at its closest approach, we're talking about unprecedented resolution of an interstellar object. For the first time in human history, we'll see surface details of something that originated in another star system. What should we expect if 3I/ATLAS is a natural comet with unusual chemistry? We should see an irregular, rocky surface marked by sublimation features, jets of material streaming away from active regions, the kind of chaotic organic landscape that characterizes natural objects formed through accretion processes over millions of years. But what if we don't see that? What if high-rise reveals geometric patterns? Reflective surfaces that don't match natural rock formations, organized structures that suggest engineering rather than natural formation? The thought keeps astronomers awake at night. Mars Express adds another dimension to the observation campaign. While HiRISE focuses on visual details, Mars Express carries spectroscopic instruments that can analyze the chemical composition of 3I/ATLAS from its unique vantage point. This spacecraft has been studying Mars since 2003, and its instruments have been fine-tuned to detect trace chemicals in planetary atmospheres and surface materials. Applied to 3I/ATLAS, Mars Express could reveal chemical gradients across the object's surface, variations in composition that might indicate layered materials or processed regions. If this object represents advanced technology, those technologies might be concentrated in specific areas, creating detectable patterns in the surface chemistry. The ExoMars Trace Gas Orbiter brings yet another perspective to the observation campaign. Originally designed to study atmospheric chemistry, TGO's instruments excel at detecting and analyzing trace gases. When applied to the expanding coma of 3I/ATLAS, these instruments could reveal chemical processes that aren't detectable from Earth-based observations. If 3I/ATLAS is releasing processed materials into space, TGO should detect the specific signatures of those processes. Industrial chemistry produces different byproducts than natural sublimation. Engineered materials outgas different compounds than natural ice and rock. The chemical fingerprints of technology are distinct from the signatures of natural phenomena. 3 spacecraft, multiple instruments, unprecedented resolution. This observation campaign represents the most comprehensive analysis ever conducted on an interstellar visitor, but it also represents something more, possibly the most important moment in the history of astronomy. The images and data we're about to receive will either confirm that 3I/Atlas is an unusual but natural object, or they'll provide evidence that forces us to reconsider our fundamental assumptions about intelligence in the universe. But there's something else that makes this observation campaign historically significant. The timing and geometry of 3I/Atlas's approach to Mars provide optimal viewing conditions that won't be repeated. This isn't just our best chance to study this particular object. It's likely our only chance to gather the detailed data needed to resolve the questions surrounding its origin. The trajectory of 3I/Atlas will carry it away from Mars and deeper into the solar system, but it won't approach any other planets at comparable distances. After this encounter, the object will begin its journey back toward interstellar space, taking its secrets with it unless we can decode them now. The pressure on the observation teams is enormous. Years of careful spectroscopic analysis have raised questions that only detailed imaging can answer. The chemistry of 3I/Atlas looks artificial. Its behavior suggests engineering. Its abundance ratios mirror industrial processes. But chemistry and behavior can be ambiguous. Images provide clarity that spectroscopy cannot. If HiRISE reveals geometric structures, organized patterns, or features that clearly indicate artificial origin, the implications will reshape human understanding of our place in the universe. We'll have documented the first confirmed artifact of extraterrestrial technology. We'll have proof that advanced civilizations exist elsewhere in the galaxy, and that their creations occasionally find their way into our solar system. But if the images show natural features, if 3I/Atlas appears to be exactly what traditional astronomy suggests it should be, then we'll face the challenge of explaining how a natural object can exhibit chemistry that looks so completely artificial. Either outcome will transform our understanding. Either we'll confirm that we've encountered evidence of extraterrestrial technology, or we'll discover natural processes that operate in ways we never imagined possible. The coming observations represent more than just another astronomical study. They represent a potential turning point in human consciousness. The moment when we either confirm our isolation in the universe or discover that we've been part of a galactic community of intelligence all along. The instruments are ready. The spacecraft are positioned. The moment of truth approaches. In the next few days, 3 mechanical witnesses will capture images and data that could answer questions humanity has been asking since we first looked up at the stars and wondered if anyone else was looking back. The universe is about to reveal one of its most profound secrets. Whether we're prepared for that revelation, that remains to be seen. But ready or not, the answers are coming. The images from Mars will either close the book on 3I/Atlas as an interesting but natural phenomenon, or they'll open an entirely new chapter in human understanding of intelligence, technology, and our place in a universe that might be far more populated than we ever dared to imagine. Here we are, at the edge of discovery, staring into the chemical signature of something that challenges everything we thought we knew about what exists in the space between stars. Nickel everywhere. Iron delayed. Abundance ratios that mirror industrial processes. Chemistry that looks engineered rather than natural. Mass that dwarfs previous interstellar visitors. Timing that seems almost too perfect to be coincidental. 3I/Atlas isn't just an unusual comet. It's a question mark written across our solar system in metals that shouldn't be there, in ratios that shouldn't exist, following patterns that shouldn't occur in nature. The more we learn about this interstellar visitor, the more profound the implications become. Each spectroscopic observation has revealed chemistry that pushes further beyond natural explanation. Each measurement has documented properties that look increasingly artificial, Each analysis has strengthened the case that we might be looking at the first confirmed artifact of extraterrestrial technology. But here's what keeps me awake at night. 3I/ETLAs is still revealing its secrets. As it continues its approach through our solar system, as our instruments gather more data, as the Mars encounter provides unprecedented resolution, we're not reaching conclusions, we're uncovering deeper mysteries. The object refuses to fit into comfortable categories. It's too massive to be typical interstellar debris, too chemically organized to be natural formation, too systematically responsive to environmental changes to be random cosmic accident, too perfectly timed in its arrival to be pure coincidence. Every answer we find raises 3 new questions. Every mystery we solve reveals 2 deeper puzzles. 3I/ATLAS isn't just challenging our understanding of interstellar objects, it's forcing us to reconsider our assumptions about intelligence, technology, and the prevalence of advanced civilizations in our galaxy. The spectroscopic evidence points toward processed materials. The abundance ratios suggest industrial chemistry. The sequential behavior indicates layered engineering. The massive scale implies technological capabilities that far exceed human achievement. Yet we're still calling it a comet, because we don't have language for what else it might be. This linguistic inadequacy reveals something important about where we stand as a species. We have sophisticated instruments that can detect artificial chemistry in interstellar objects. We have theoretical frameworks that can recognize evidence of advanced technology, but we don't have conceptual structures that allow us to process what these discoveries mean for our understanding of the universe. We're in the position of archaeologists who have uncovered artifacts from a civilization so advanced that they can't immediately recognize the objects as technology. The chemistry is clear, the measurements are precise, the data is undeniable, but the implications are so vast that we struggle to articulate what we've found. The coming observations from Mars will provide clarity on some questions while undoubtedly raising others. If HiRIS reveals geometric structures or organized patterns, we'll have visual confirmation of what the chemistry has been suggesting. If the images show natural features, we'll face the challenge of explaining how natural processes can produce signatures indistinguishable from advanced technology. But regardless of what the Mars encounter reveals, 3I/ATLAS has already transformed our understanding of what's possible in interstellar space. It has demonstrated that objects with impossible chemistry can survive the journey between star systems. It has shown that interstellar visitors can exhibit properties that challenge fundamental assumptions about natural formation processes. Most importantly, it has opened our eyes to the possibility that we've been surrounded by evidence of advanced intelligence all along, but we were too primitive to recognize what we were looking at. This realization should humble us. For decades, we've searched for signs of extraterrestrial intelligence by listening for radio signals, looking for artificial structures around distant stars, analyzing atmospheric compositions of exoplanets for signs of industrial activity. We've been searching for intelligence that operates the way we operate, uses technologies that resemble our technologies, sends signals that we would send. But 3I/ATLAS suggests that advanced intelligence might operate on scales and use approaches that we're only now becoming sophisticated enough to detect. Instead of sending radio messages, they might create artifacts that carry information in their chemical composition. Instead of building megastructures, they might engineer materials that reveal their properties when exposed to stellar radiation. Instead of announcing their presence, they might leave evidence that we can discover when we develop the right instruments. The unfinished mystery of 3I/ATLAS extends beyond the object itself to questions about the nature of contact between civilizations, separated by vast distances and potentially enormous differences in technological sophistication. If this object is artificial, it represents a form of communication that operates on timescales measured in millions of years. It suggests intelligence that can create objects capable of surviving interstellar travel while maintaining their ability to reveal information under specific conditions. This is communication that doesn't require active participants on both ends. It's archaeology in reverse. Advanced civilizations leaving artifacts for primitive species to discover when they become sophisticated enough to recognize what they've found. The implications ripple through every aspect of human understanding: science, philosophy, religion, technology, social structures. Everything we thought we knew about our place in the universe needs to be reconsidered in light of the possibility that we're not alone, have never been alone, and are surrounded by evidence of intelligence that we're only now learning to recognize. But perhaps the most profound implication of 3I/ATLAS is what it suggests about the future. If advanced technological civilizations are common enough that their artifacts occasionally wander into our solar system, then we might be entering a phase of development where such encounters become routine rather than extraordinary. Every unusual object that enters our solar system becomes a potential archaeological site. Every anomalous chemistry reading becomes a possible signature of intelligence. Every technological advancement that improves our observational capabilities increases the likelihood that we'll recognize evidence of advanced civilizations that has been surrounding us all along. The mystery of 3I/ATLAS isn't finished because it's not just about one object. It's about the transformation of human consciousness from a species that assumes it's alone to a species that recognizes it's part of a galactic community of intelligence. This transformation has only just begun. As 3I/ATLAS continues its journey through our solar system, as we gather more data, as we develop more sophisticated analytical techniques, we'll learn not just about this particular object, but about the nature of intelligence in the universe. We'll discover whether advanced civilizations are rare anomalies or common features of galactic evolution. We'll learn whether artifacts like 3I/ATLAS are isolated curiosities or part of a vast network of intelligence that spans interstellar distances. The unfinished mystery continues to unfold. Each observation reveals new questions. Each measurement opens new possibilities. Each analysis points toward conclusions that challenge our fundamental assumptions about reality. 3I/ATLAS has shown us that the universe is stranger than we imagined, more populated than we assumed, more interconnected than we believed possible. The chemistry of one interstellar visitor has opened the door to possibilities that could transform human civilization's understanding of its place in the cosmic community of intelligence. The mystery isn't finished because we're not ready for it to be finished. We're still learning what questions to ask. We're still developing the conceptual frameworks needed to process what we're discovering. We're still becoming the species we need to be to understand what the universe has been trying to tell us all along, but the evidence continues to accumulate. The chemistry continues to point toward artificial origin. The implications continue to expand beyond astronomy into fundamental questions about intelligence, technology, and humanity's future among the stars. 3I/ATLAS leaves us with more questions than answers, but they're the right questions. Questions that will drive human development for generations. Questions that will reshape our understanding of what's possible in the universe. Questions that will guide us toward a future where we might finally understand that we have never been alone. The heavy metal comet from beyond our solar system has delivered more than just unusual chemistry. It has delivered the possibility that we are part of something much larger, much more sophisticated, and much more wonderful than we ever dared to imagine. The mystery continues. The implications expand. The transformation of human consciousness has only just begun.